Look up at the night sky. What do you see? A dazzling tapestry of stars, each a distant sun. The universe is vast, filled with billions upon billions of these celestial wonders. They twinkle and gleam, captivating us with their distant light. But have you ever wondered what these stars are and what makes them shine? Stars are not just points of light. They are massive balls of hot, glowing gas, primarily hydrogen and helium. They are cosmic furnaces, powered by a process called nuclear fusion that occurs deep within their cores. The immense gravity of a star pulls all its material inward, creating intense pressure and heat at the center. It is under these extreme conditions that the magic of fusion takes place. Stars are born in vast, cold clouds of gas and dust scattered throughout galaxies. These clouds, known as nebulae, are the stellar nurseries of the cosmos. Gravity is the driving force behind star formation. Within a nebula, gravity slowly draws clumps of gas and dust together. As these clumps grow larger, their gravitational pull strengthens, pulling in even more material. This process of gravitational collapse releases a tremendous amount of energy, heating the contracting cloud of gas and dust. As the temperature and pressure at the center of the collapsing cloud continue to rise, a protostar is formed. A protostar is a young developing star that is still gathering mass from its surroundings. It emits infrared radiation as it heats up, but it is not yet hot enough to ignite nuclear fusion in its core. The life of a star is a delicate balancing act between two powerful forces, gravity and nuclear fusion. Gravity, as we've seen, is the force that pulls everything together. It's what caused the star to form in the first place, and it's constantly trying to crush the star down into a smaller and denser object. Opposing gravity is the outward pressure from nuclear fusion. Fusion is the process where lighter atomic nuclei combine to form heavier ones, releasing an enormous amount of energy in the process. In the core of a star, hydrogen atoms are fused into helium, releasing a torrent of energy in the form of light and heat. This outward pressure from fusion pushes against the inward pull of gravity, creating a delicate equilibrium that keeps the star stable. Once a protostar becomes hot and dense enough, it undergoes a remarkable transformation. This process is the beginning of a star's life, a journey that spans billions of years. The protostar, which is essentially a cloud of gas and dust, collapses under its own gravity. As it collapses, the material in the center heats up and becomes denser. Eventually, the temperature and pressure in the core becomes so extreme that nuclear fusion ignites. This is the moment when a star is truly born. The fusion process involves hydrogen atoms fusing together to form helium, releasing a tremendous amount of energy in the process. This energy is what makes the star shine so brightly. The star then enters a long, stable period of its life called the main sequence. During this phase, the star maintains a delicate balance between the gravitational forces pulling inward and the pressure from nuclear fusion pushing outward. This balance allows the star to remain stable for millions to billions of years. Our Sun is a main sequence star, and it has been shining brightly for about 4.6 billion years. It is currently in the middle of its main sequence phase, providing the energy necessary to sustain life on Earth. The Sun's surface is a dynamic place, with solar flares and sunspots constantly changing its appearance. During this phase, the star fuses hydrogen into helium in its core, generating the energy that makes it shine. This process is incredibly efficient, allowing the star to produce a vast amount of energy from a relatively small amount of fuel. The energy generated in the core travels outward, eventually reaching the star's surface and radiating into space. The length of time a star spends on the main sequence depends on its mass. More massive stars have more fuel to burn, but they also burn it much more quickly. This means that they have shorter lifespans compared to smaller stars. Massive stars have much shorter lifespans than smaller stars. They can burn through their hydrogen fuel in just a few million years, whereas smaller stars can last for billions or even trillions of years. This rapid consumption of fuel leads to a more dramatic and shorter life cycle for massive stars. This is because massive stars burn through their hydrogen fuel much faster due to the intense pressure and heat in their cores. The core of a massive star is a cauldron of nuclear reactions, with temperatures reaching millions of degrees. This extreme environment accelerates the fusion process, causing the star to consume its fuel at a much faster rate. Smaller stars, on the other hand, sip their fuel slowly, and can live for billions or even trillions of years. These stars, often referred to as red dwarfs, are much cooler and less luminous than their massive counterparts. Their slow and steady fusion process allows them to shine for an incredibly long time, making them some of the most enduring objects in the universe. As a star ages, it eventually runs out of hydrogen fuel in its core. Without the outward pressure from fusion to counteract gravity, the core begins to contract and heat up. This process marks the beginning of a dramatic transformation in the star's life cycle. The core, now devoid of its primary fuel, starts to collapse under its own gravity, causing the temperature to rise significantly. This increase in temperature is a crucial phase in the star's evolution, setting the stage for the next series of events. This heating causes the star's outer layers to expand outward, and the star swells up to many times its original size. The outer layers, now pushed by the intense heat from the core, begin to balloon outward. This expansion is so vast that the star can grow to hundreds of times its original diameter. The once compact and stable star now becomes a massive, bloated giant, dominating its region of space. As it expands, it cools and its color shifts to red. This cooling occurs because the energy from the core is now spread over a much larger surface area. The star's surface temperature drops, and it takes on a reddish hue, a stark contrast to its former, hotter state. This color change is a visual indicator of the star's new phase in life. The star has now become a red giant. This phase is one of the most fascinating in stellar evolution. The red giant phase is characterized by a delicate balance between the gravitational forces pulling inward and the thermal pressure pushing outward. This balance is temporary, but it defines the star's structure during this period. Red giants are cool but luminous stars. Despite their lower surface temperatures, they shine brightly in the night sky. This luminosity is due to their enormous size, which allows them to emit a significant amount of light. The sheer volume of the star compensates for its cooler temperature, making it one of the most prominent objects in the sky. They are cool because their surface temperatures are lower than main sequence stars, but they are luminous because of their enormous surface area. The vast surface area of a red giant means that even though each square meter emits less light than a smaller, hotter star, the total light emitted is immense. This makes red giants some of the most luminous stars in the universe. One of the most famous red giants in the night sky is Betelgeuse, a bright red star in the constellation Orion. Betelgeuse is a prime example of a red giant, easily visible to the naked eye. Its distinct red color and brightness have made it a subject of fascination for astronomers and stargazers alike. Located in the shoulder of the Orion constellation, Betelgeuse is a key feature of this well-known star pattern. Betelgeuse is nearing the end of its life, and astronomers believe it could explode as a supernova at any time. This impending supernova is a topic of great interest and speculation. When Betelgeuse finally explodes, it will be one of the most spectacular events visible from Earth. The explosion will outshine entire galaxies for a brief period, leaving behind a nebula and possibly a neutron star or black hole. This dramatic end will mark the final chapter in the life of a star that has captivated human imagination for centuries. For stars like our Sun, which are classified as medium-sized stars, and those that are even less massive, the journey through their life cycle is a fascinating and complex process. These stars spend the majority of their lives fusing hydrogen into helium in their cores, a phase known as the main sequence. However, this stable period doesn't last forever. Eventually, these stars exhaust the hydrogen fuel in their cores, causing them to leave the main sequence and enter the red giant phase. This phase marks the beginning of their end. During this time, the core contracts under gravity, while the outer layers expand and cool, giving the star its characteristic red hue. As the core continues to contract, it eventually becomes so dense that a new type of pressure, called electron degeneracy pressure, halts further collapse. This pressure is a quantum mechanical effect that arises because electrons, which are fermions, cannot occupy the same quantum state. This quantum mechanical behavior of electrons, known as the Pauli exclusion principle, prevents them from occupying the same energy levels. As a result, the core stabilizes and stops contracting, even though it is incredibly dense and hot. Meanwhile, the outer layers of the star are expelled into space, forming a beautiful glowing cloud of gas and dust called a planetary nebula. This nebula is illuminated by the intense radiation from the hot core, creating stunning and intricate patterns in the surrounding space. At the center of this nebula lies the remnant core of the star, a small, incredibly dense object called a white dwarf. This white dwarf is the final evolutionary state of stars like our Sun, representing the last stage in their life cycle. White dwarfs are about the size of Earth but contain a mass comparable to the Sun. This means they are incredibly dense, with a single teaspoon of white dwarf material weighing tons. Despite their small size, they have a gravitational pull that is thousands of times stronger than Earth's. When white dwarfs first form, they are incredibly hot, with surface temperatures reaching up to 100,000 degrees Celsius. However, they gradually cool down over billions of years, fading away as stellar embers. This cooling process is slow and steady, and as they lose their heat, they become dimmer and less visible, eventually turning into cold, dark remnants known as black dwarfs, although the universe is not old enough for any black dwarfs to exist yet.